All right, so we're going to start looking at polynomial functions. And so we're in this unit, we're going to look at long division and synthetic division to divide polynomial expressions by binomial expressions. And then we're going to use that to factor a polynomial and then to determine the zeros of those functions. And so the zero is where they cross the x-axis on our graph. All right, so let's just have a bit of a recap on a polynomial function. This might be a little confusing, but a has to be a value of a real number, and then x to raised to some power is going to be different various degrees of our polynomial. And a in this term, or in this case, is going to be a constant term, and x is going to be a coefficient of a higher power. And if we have a higher power, then that could be like x to the power of 4, x to the power of 5, x to the power of 3, any of those. Usually something higher than degree 2. Now let's look at this example down here where we're considering this polynomial. X to the power of 4 plus 7x cubed minus 8x squared plus 5. And so we want to state what the degree of the polynomial is. Now, we could look at this and we could look at any of these exponents and say that there's various degree. But when we're seeing the degree of a polynomial, especially if I have one that is 4 terms long, 1, 2, 3, 4, separated by my operations of positive and or of plus and minus, then I always go with the highest exponent for my degree of my polynomial. So that would be the degree of this polynomial would be 4. The leading coefficient, well, the leading coefficient, that goes with the highest degree. So if I have x to the power of 4, and if there's no value in front of x, then that means that the leading coefficient would be 1. And the constant term, that's going to be the term that has no variable attached to it. And so in this case, the only term that has no variable is 5. All right, let's look at the next few examples. And I'm only going to do the first 3 here. And you can do these ones by yourself. And we want to express expressions containing roots of variables, negative or fractional powers of a variable, or any coefficient which is non-real are not polynomial functions. So again, you might want to read that over to yourself to make sense of it. But if I have an expression, and if it has the root of a variable, this contains roots of variables. So for example, square root x, negative or fractional powers of a variable. So if I have x to the negative 2 or x to the 1/2, something like that, or any coefficient which is non-real, so like square root of negative 3 or something, then those are not going to be a polynomial function. All right? So let's take a look at this. Say whether or not the following are polynomial functions, and if they are, then if they are not polynomial functions, explain why they are not. Well, this one is not, because if we look at the example, anything that has a power, a variable that has a fractional power, so x to the power of 1/2, is not a polynomial. X to the power of 1/2 is not a polynomial function. Let's look at C. Well, square root of 17, that is a real number, and everything else checks out as well, so this is a polynomial. E, and maybe I'll do a couple more. I'll point out, well, actually, all of these ones, the answer is going to be no, they're not polynomials, and I'll go through those bit by bit. And this one is, yes, that is a polynomial function. Even though I have the square root of a variable with a fraction, we can break that down, and we can say that that's equal to square root of 3 times x. But this one is not a polynomial function because I have a negative power in this example, so that can't be. This one over here, it's also not a polynomial function because I can't have the square root of x cubed. If I have the square root of x cubed, that's x to the power of 3/2, which is a fractional power on a variable. And this last one, no, I can't, because I have a non-real number as a coefficient, so that also cannot be a polynomial function. Next, let's take a look again at degrees, leading coefficients, and our constant terms. So all we need to do here is, sometimes a polynomial function can be in a disguised form. So let's look at what that means. So we want to state the degree, the leading coefficient, and the constant term for each polynomial function. Now the reason it's saying that it's in a disguised form is because if we take a look at this, it's kind of mixed up, right? Like my degree on this polynomial is not going to be 2, even though that's at the front. My degree of this polynomial is actually going to be a degree of 3. And the leading coefficient, remember, is the one that's attached to the highest degree. And so my leading coefficient is not going to be 34, but instead it's going to be negative 25. And my constant is going to be negative 39. Now, in this example, we have a polynomial that's been factored. And so we have to we have to expand this by foiling it, or applying the distributive method. And if we do that, we're going to get 10x squared plus 35x minus 2x, so 33x, and minus 7. So this is again in disguised form because we had to do a little bit of work and kind of translate what this actually means. So my degree here is going to be 2. My leading coefficient is attached to my highest degree, so 10. And my constant is going to be negative 7. Now in this next example, we want to kind of do the same thing. We want to determine the degree, the leading coefficient, and the constant term without expanding. And we want to verify the results that we get here by then expanding and simplifying the polynomial. Okay, so let's take a look. If I take a look at this, basically what we're trying to do is kind of estimate what we're going to get. So we want to estimate the degree, the leading coefficient, and the constant term. All right, if I take a look at this right now, I know that I'll have x squared, and I'll have another x. I have another x squared, and if I multiply those x squareds, so x squared here by x squared, then my degree would be x to the power of 4. So my degree of this coefficient would be 4. The leading coefficient, well, again, if I were to, so when you do any of this, you kind of are expanding it, right? Like if I were to go 2 times 3, and then again times 5 for my leading coefficient, since those are going to be attached to my highest power, and it's going to be 2, and squared, we're going to get 90. So 2 times 9 times 5. The constant term, what we're looking at is anything that is not attached to a variable. So 2, I'm going to end up multiplying that 2 by negative 1, and that's squared, and I'm going to multiply that by 1, so my constant term should be 2 for this one. And you can do the exact same thing for this side here. I won't do that in the video here, but it's pretty self-explanatory. And so now what we want to do is we want to expand this. So we want to actually expand and simplify. So let's start with this side over here. I'm working with 2, and if I square this portion, I'm going to end up with 9x squared minus 6x plus 1, and I'm going to multiply that by 5x squared minus x plus 1. Now I'm not going to multiply everything by 2 yet. Instead, what I want to do is I want to apply my distributive properties all the way across. So I'm going to end up with 45 x to the power 4 minus 9x cubed plus 9, that's cube, 9x squared minus 30x cubed, if I go in this direction now, plus 6x squared minus 6x, and plus 5x squared minus x plus 1. Alright, so all I did was distributed everything across the brackets. I FOILed it, and now I need to add my like terms. So I know it's going to be 2 times 45x to the power 4 minus 9x cubed, 30x cubed, minus 39x cubed, 9x squared, 6x squared, 5x squared, and I think that is it. And I get plus 20x squared, negative 6x, and negative x will give me negative 7x, and I get positive 1 for my constant term. And so if I multiply everything by 2 now, I'm going to end up with 90x to the power 4 minus 78x cubed plus 40x squared minus 14x plus 2. And so now let's compare to what we had earlier. I had my degree of 4, check. My leading coefficient was, I think I did say 90 earlier, so 45 times 2, yeah, 90. I should have wrote 90, I think I said 90, but I didn't write it down. And then my constant was 2. So everything checked out. Now, let's look at example number 5 here. Consider the polynomial function px is equal to 7. Explain why the polynomial function px equals 7 has a degree of 0. And then explain why this type of function is called a constant function. Well, this has a degree of 0 because we can say that p to the power of x, if p to the power of x is equal to 7, we can say that this can also be written as p to the power of x is equal to 7 to the power of x to the power of 0. And if this exponent here is 0, that means that this is actually equal to 7 times 1, or just 7. So degree 0 there. Explain why this is a constant function. So this is a constant function because if I have any value of x, let's say x equals 2, so p to 2 is equal to 7 to the power of 0, that is still going to be 7 times 1 is still going to equal 7. So there's no way we can actually change this value if we have a degree of 0. So no matter the value of x, the value of p to the power of x is going to stay the same. All right, let's now we want to work at classifying polynomials. And we can do that in a few ways. By number terms, and you should already, this should be familiar with you. We have a monomial, that's one term, so if I just have x squared, a binomial, that would be 2 terms, so x squared plus 1. A trinomial would be, let's say, x squared plus 6x plus 9. And then something with more than 3 terms is generally considered a polynomial. So we wouldn't call it a tetranomial or anything like that. It would just, anything higher than 3 is a polynomial. Another way we can do that is by degree. And so if I have a constant term, remember in the last example, that had a degree of 0. If it was linear, it will have a degree of 1. So one really common one is y is equal to mx plus b. If you look at that, your x value there, that has a degree of 1. Quadratic, well, we looked at those already. So above, that's a degree of 2. So this would be quadratic. If you type this into your calculator, you should get a nice parabola. Cubic terms, degree 3 would be something like that, and then a quartic term would have a degree of 4, and then it goes up to quintic and anything higher than 5 still has a name. Now I'm going to complete the chart. what we want to do is name the degree. So we're going to go 1, 2, 3, 4, 5. So we're probably going to start at 0 here. And yeah, if I have p to the power of x is equal to c, remember that if I have x to the power of 0, that's still just going to equal c, because x to the power of 0 is just equals 1. So that degree is going to be 0. And anything with a degree of 0 has a constant term. This is linear. The degree is 1. This is a degree of 2. So that's quadratic. Degree of 3 is cubic. And I'm looking at these degrees right here. And degree of 4 is quartic. All right, so this is going to be the new one for you, the quartic functions. All right, research the name for polynomials of degrees 5 through 10. All right, this is going to be one that you just Google it, right? Google it. But degree 5 is quintic. Degree 6 is hexic or sextic. Degree 7 is septic or heptic, so it's kind of using French here. Degree 8, hopefully you know, is octic. Degree 9, nonic, and degree 10 would be decic. All right, but I'm not going to write those down. You can, if you're wondering about spelling, I think you should go look those up. Now, we can also classify them by the type of coefficients that they have. So polynomial functions can be classified according to their coefficients, and there's a number of examples below. But if I have something 3, 5, and 7, this is an integral polynomial function, where if you look at all of these are all integers. And actually we're not looking at that one there, but all of these are integers. If I have 3, 2/5, and 1, that's a rational polynomial function. If I have something with square roots, that's considered a real polynomial function. And lastly, let's take a look at these examples. In each case, we want to write a polynomial satisfying the following conditions: well, trinomial, quartic, and integral. So trinomial, that tells us that we have 3 terms. So there's 3 terms going to be involved. Quartic, that tells us that we have a degree of 4. And then integral, that means all of our coefficients are going to be integers. And so you can just make one up. You don't have to use the one I'm using. You can just make up anything here, really. So trinomial, I need 3 terms, which means I need 2 signs busting it up. And I'll have that as a 7. And this one, if I want it to have a quartic term, remember that means I need to have a degree of 4. Trinomial x4 plus x minus 7. Well, let's make it x cubed. There we go. 3 terms. 1, 2, 3. And I'll make it more integral, and I'll put a 2 in front of there. P of x is equal to a binomial term that's linear and real. With binomial, there's 2 terms. If it's real, that means it has to have a square root as one of its coefficients. So let's go square root of 5x. And it's linear, so it has a degree of 1. And let's make it square root of 5x plus 7. So that satisfies all my conditions. And so monomial, quadratic, and rational. So remember, rational, it has fractional coefficients, so let's go 1/3. If it's quadratic, then that means the degree is going to be 2, and there's 1 term, so our terms are satisfied. All right, so if p of x is equal to negative 3x squared plus ax plus 8, and p of 1 is equal to negative 9, then find the value of a. Okay, so in this case, we're told that x is equal to 1, and we know that p of x is equal to negative 9. So we're going to have to combine these two conditions here. So p of x is negative 9, and I know that negative 9 is equal to negative 3, but x is equal to 1. 1 squared plus a times 1 plus 8. Negative 9 is equal to negative 3 plus a times 1 is a plus 8. I'm going to be left with negative 9 is equal to 5 plus a, and a is equal to 14. Now the next example, we're going to do the exact same thing, and I think you could probably handle this on your own, but I'm just going to get you started. So in the first one, determine the values of a and b in p of x is equal to negative 2x squared plus ax plus b if p of 2 is equal to negative 18 and p of negative 3 is equal to negative 13. All right, now again, we want to start with our known values. So I know that x is equal to 2 when p of x is equal to negative 18. And so I would begin by solving this. I would substitute my values in. So negative 18 for p of x is equal to negative 2 times 2 squared plus a2 plus b. Negative 18 is equal to negative 2 times 4 plus 2a plus b. Negative 18 is equal to negative 8 plus 2a plus b. And I get, if I balance this out, 2a plus b is equal to negative 10 if I bring that to the other side. Okay, now what you need to do is you have to do the same thing for the other side of the equation. Well, not for the other side, but you have to combine these terms. And so what I mean by that is, if for the second set x was equal to negative 3 when p of x is equal to negative 13, I'm going to plug this into my equation. So negative 13 is equal to negative 2 times negative 3 squared plus a times negative 3 plus b. Negative 13 is equal to negative 2 times 9 and minus 3a plus b. Negative 2 times 9 is negative 18 minus 3a plus b, and I get, if I bring my 3a and my b to the other side and my 13 to this side, I get negative 5. So the next thing we can do is just combine these terms. And so I have 2a plus b is equal to negative 10, and 3a minus b is equal to negative 5. If I add together all my like terms, I'm going to end up with 5a is equal to negative 15, and I can solve for a, that is equal to negative 3. Now that I know what my value of a is, I can determine what my value of b is going to be.